This tells us that we have a dataset X with 100 samples and 5 features. I'm thinking of each sample as a different person, and each feature as a different characteristic, like height, weight, age, etc. Similarly, this is the response dataset. It has the same 100 samples as dataset X, but now instead of 5 characteristics, each sample only has 2 measured outcomes. For example, maybe Y shows their blood pressure, 2 values, systolic and diastolic. We're trying to use X to predict Y. This problem uses partial least squares regression, PLSRegression, a statistical method designed to find relationships between two datasets when both have multiple variables and are correlated. We are evaluating its performance. I use cross-validation to assess how well the model generalizes to new, unseen data. I split the data into 5 parts. The model is trained on 4 parts and tested on the remaining part. I repeat this process 5 times, testing on each of the 5 parts. This gives a more robust evaluation of the model than training and testing on a single split. These are the R-squared values I obtained from the 5-fold cross-validation. R-squared measures how well the model fits the data, ranging from 0 to 1, with 1 indicating a perfect fit. So, each number represents how well the model performed in each of my 5 tests. The higher the R-squared, the better the fit. This is one of the multiple-choice questions. I'm asked to calculate the average R-squared across the 5 folds and determine if the statement is true or false. I need to average the 5 R-squared scores. I'm evaluating a partial least squares regression model. This model is used to find relationships between 2 datasets, one with predictors, X, and one with responses, Y. I'll be checking how well it predicts. I'm using a technique called 5-fold cross-validation to get a good idea of the model's performance. I'm splitting my data into 5 groups. 4 groups will be used to train the model, and 1 group will be used to test how well it predicts new data. I then repeat this process 5 times, using each group once as the test data. This prevents the model from overfitting and gives a more accurate assessment. These are the results I got from my 5-fold cross-validation. Each number represents how well the model performed on each of the 5 test sets using the R-squared metric. R-squared tells me what proportion of the variance in the response variable is explained by the model. Higher is better. Notice how the scores vary a bit, showing some inconsistencies. Now it's time to see if you understand. Which of the provided statements correctly describe these results? Let's see how well you did. This statement checks if you can calculate the average R-squared. To do this, I add up all the R-squared values and divide by the number of folds, 5. It's a simple average. This statement asks if the R-squared values show significant variation between the folds. Look at the range of scores. Does it indicate inconsistency or stability? This statement relates to how the number of components in PLSRegression influences the R-squared. Remember, more components don't always mean a better model. Overfitting is a concern. This statement explores the trade-off between model complexity and performance. Simpler models, fewer components, are generally less prone to overfitting but may sacrifice some accuracy. I see 5 R-squared scores here, representing the model's performance on each of the 5 folds in the cross-validation. Each number shows how well the model predicted the response variable, Y, on a different portion of the dataset. A higher R-squared value means a better fit. Notice the variation between them. This shows how consistently the model performs across different data subsets. This is a great way to evaluate a model. Instead of testing it on one random subset of the data, which might not be totally representative, you divide your data into 5 equal portions. Then, I train the model on 4 portions and test it on the remaining portion. I repeat this process 5 times, using each portion as the testing set once. That gives me a more robust estimate of how the model will perform on completely new data. This is the response data, the thing I'm trying to predict. It has 100 data points, each with 2 response values. I will aim to use my model to predict these values using the predictor variables from dataset X. The goal is to evaluate how well this partial least squares regression model works. I'm using cross-validation and the R-squared metric to figure that out. PLSRegression tries to find relationships between 2 datasets X and Y where both might contain many variables. To get this value, I added all 5 R-squared values together. 0.85 plus 0.78 plus 0.92 plus 0.80 plus 0.88, and divided that sum by 5, the number of folds. The average tells me the overall performance of my model across all the folds in cross-validation. It's a pretty good performance, showing that on average, the model explains around 85% of the variance in the response variables. I'm using partial least squares regression, a technique that finds the best way to relate two datasets. I'm evaluating how well my model predicts. My predictor dataset has 100 samples and 5 features or variables. I'll use these to predict values in the next dataset. My response dataset also has 100 samples but only 2 variables. I want to predict these values using the features in the previous dataset. To avoid overfitting and get a reliable estimate of the model's performance on new data, I'll split the datasets into 5 groups. I will train the model on 4 groups and test on the remaining group. I'll repeat this process 5 times using a different test group each time. These are the R-squared values from each of the 5 cross-validation folds. R-squared, which is a measure between 0 and 1, represents the goodness of fit. A higher R-squared implies a better fit. These values tell me how well my model performed in each fold. Let's analyze these scores. Based on the R-squared scores from the cross-validation, I need to determine which statements about my model's performance are correct. I'll calculate this by adding all the R-squared scores and then dividing by 5. The average gives me an overall measure of the model's performance across the different dataset splits. I'll look at the range of R-squared values. The variation tells me how consistent the model performs. A larger range suggests inconsistency. Increasing components in PLSRegression can sometimes improve the R-squared score but can also lead to overfitting, reducing how well it generalizes. It is not a guarantee. Using fewer components creates a simpler model, which means a lower risk of overfitting. However, it may not achieve the highest R-squared on the training data. This is a classic trade-off between model complexity and generalization. I'm using PLSRegression, a statistical method that helps me find the best relationship between my predictor variables, x, and my response variables, y. It's particularly useful when I have many predictors and they are correlated. These are the R-squared values I got from my 5-fold cross-validation. R-squared tells me how well my model fits the data. A higher value is better. The values here range from 0.78 to 0.92. Showing some variability in model performance across the different folds. I calculated this by adding up all the R-squared values and dividing by the number of folds, 5. It gives me a single overall measure of how well the model performs on average. In this case, the average is approximately 0.85. This is my dataset of predictor variables. It contains 100 observations and 5 predictor variables. This is my dataset of response variables. It also has 100 observations, but it has 2 response variables that I'm trying to predict using the variables in X. I'm using partial least squares regression, PLSRegression, a statistical method that helps me find the relationship between 2 datasets, X, predictors, and Y, response, even when they have many variables and are highly correlated. I'm evaluating this model's performance. Dataset X contains 100 samples, each described by 5 features or predictor variables. Dataset Y contains the corresponding 100 response values, each having 2 different aspects. To make sure my model generalizes well to new data and isn't just memorizing the training data, I use 5-fold cross-validation. I split my data into 5 groups. Then, I train my model 4 times on 4 of these groups and test it on the remaining group. I repeat this process 5 times, using each group as the test set once. This gives me a more reliable estimate of the model's performance. These are the R-squared scores from each of my 5 cross-validation folds. R-squared measures how well my model explains the variance in the response data. A higher R-squared is better, indicating a better fit. To get a single performance metric, I average the 5 R-squared scores. I add them all up and divide by 5. 0.85 plus 0.78 plus 0.92 plus 0.80 plus 0.88. 5 equals 0.846, which is approximately 0.85. PLSRegression uses components to model the relationship between X and Y. Fewer components make the model simpler. This can prevent overfitting, where the model performs well on training data but poorly on new data. However, it might also reduce accuracy if the relationship is complex and requires more components to capture it. That's not always true. While adding components can improve the R-squared score on the training data, it increases the risk of overfitting, and might actually reduce the R-squared score on new, unseen data. The R-squared scores vary from 0.78 to 0.92. This variation suggests that the model's performance is not stable across different subsets of the data. As we calculated, the average R-squared is about 0.85. This is a summary measure of model performance across all folds.